Systems design is the critical phase where we translate a business need into a technical blueprint for a computer system. This stage acts as the bridge between understanding a problem and actually constructing a solution. It is the step that must logically follow a thorough systems analysis. In the analysis phase, we ask what the system must do to solve a business problem, business requirements, user needs. In the design phase, we pivot to ask how the system will accomplish those goals. Design is fundamentally about making specific, concrete technical decisions that will shape the final product and its operational life. A clear and well-considered design is the foundation of a successful project. It provides the development team with a detailed map to follow, which dramatically reduces the chances of building the wrong thing or making costly mistakes late in the process. This detailed plan helps project managers create more accurate estimates for time. This detailed plan helps project managers create more accurate estimates for financial resources. A good design is not an overly rigid or complex document. Instead, it is clear, comprehensible, and engineered to be adaptable. It must be resilient enough to accommodate future changes without requiring a complete overhaul of the entire system, ensuring longevity and a lower total cost of ownership. So, what exactly is systems design? It is the process of creating a detailed physical plan for a software-based solution. Architecture, components, modules, interfaces, data. It moves from the logical models created during analysis, which represent the business view, to physical models that represent the technical implementation. In essence, analysis deals with the problem domain, focusing on business logic and rules. In contrast, design deals with the solution domain, focusing on technologies, platforms, practicalities of implementation. The output of design is a complete specification that a team of programmers can use to build the actual system. The primary goals of any good systems design are straightforward yet vital for success. Ensure the system functions correctly. Meet all specified business requirements. It must also be designed for maintainability, meaning it should be easy to update, easy to fix, easy to enhance. Security is another paramount goal. The design must incorporate measures to protect the system and its data from unauthorized access and other threats. Performant, reliable. Stay within the project's budget. Cost effectiveness throughout the design process. There are many established methodologies or approaches for designing a computer system. Each approach provides a different framework and emphasizes different aspects of the design process. These methods can be broadly categorized into two families: more structured, plan-driven approaches, more agile, adaptive approaches. Structured methods, like modern structured design, information engineering, are excellent when requirements are stable and well understood. Agile methods, such as prototyping, rapid application development, suit projects with evolving requirements and heavy user feedback. Modern structured design advocates a top-down, modular approach. Break a large system into smaller, manageable modules. Each module performs a single, well-defined function. High cohesion. Modules should have low coupling, be independent from each other. That separation makes the system easier to develop, easier to test, easier to maintain because changes have fewer ripple effects. This decomposition gives a clear, organized system structure. Information engineering emphasizes data as the central, stable business element. Business processes may change often. Fundamental data entities are more stable. Customers, products, orders. Start design with a detailed data model, often an entity relationship diagram. Design system processes to interact with this stable data foundation. Data-centric design ensures consistency and integrity across the enterprise. It's powerful for large organizations building integrated information systems where data sharing is paramount. In contrast, object-oriented design offers a different structure. It bundles data and processes together into objects. Each object is a self-contained unit representing a real-world entity. Objects contain data, attributes that describe them, and methods, behaviors they can perform. Example, A customer object contains data like a name and address, and methods like place order or update address. OOP promotes code reuse via inheritance and polymorphism. Resulting systems are more flexible, more scalable, and easier to modify over time. Rapid application development is a high-speed methodology that combines several techniques: prototyping, structured methods, user-centric workshops. It emphasizes an iterative development cycle and powerful tools. Speed is the advantage, but architectural quality can suffer. Choosing to build a system in-house is a strategic decision that gives an organization maximum control over the final product. This build approach is often selected when the required functionality is highly unique to the business and cannot be met by any off-the-shelf software. It is the right path for creating a system that provides a distinct competitive advantage, as the software is tailored precisely to the company's proprietary processes and strategic goals. While this path offers unparalleled flexibility, it also carries the full responsibility for the project's success or failure. The organization must possess or acquire the necessary technical expertise, resources, management discipline to see the project through. The primary benefit of the in-house build strategy is the perfect alignment between the software and the business needs, leading to gains in efficiency, user adoption, competitive differentiation. Furthermore, you own the intellectual property, giving you complete control over the system's future evolution. You can add features, modify workflows, integrate with other systems on your own timeline. However, the build strategy comes with significant risks and responsibilities. Higher upfront cost in time, money, personnel, risk of budget overruns and schedule delays, and the burden of long-term maintenance, support, upgrades. As technology evolves, you will be responsible for keeping the system up to date, secure, compatible with new platforms, requiring sustained commitment of skilled technical staff. A classic example: a large investment bank developing a proprietary algorithmic trading platform designed for extreme speed, reliability, tailored exactly to strategies where substantial profits justify high initial and ongoing costs. Section 5. Tasks for the in-house build. When you commit to building in-house, the design phase involves detailed technical tasks to create a complete blueprint for the development team. First task: design the application architecture, the high-level structure of the system. Make fundamental technology choices: programming languages, frameworks, server infrastructure. Decide on architectural patterns: layered architecture, microservices architecture, client-server model. Define how major components are organized and communicate. Form the skeleton for the application. Translate logical models from analysis into physical models. For example, a logical data flow diagram converted into a physical data flow diagram specifying file formats, database tables, communication protocols. Transform logical data models into a physical database schema optimized for the DBMS. Create detailed schema-defining table, column, data type, relationship. Design indexes. Enforce validation. Establish keys. Plan access controls. Backups. Disaster recovery. A well-designed database supports performance, reliability, and security. Document and package the design into specifications for programmers. Design the system interface, user-facing screens, interfaces with other systems. Create wireframes. Build prototypes for user inputs and outputs. Define dialog flow for user interactions. Write detailed specifications for each program or module. Describe the module's purpose. List inputs. Specify processing logic. Define outputs. Specify error handling. Update the project plan with timelines and cost estimates. Provide a clear roadmap for construction. So, that's the set of tasks you need to, get right before coding begins. Opting to buy a commercial off-the-shelf software package. A commercial off-the-shelf package is another common strategy for acquiring a new system, This buy approach, also known as procurement, involves purchasing, leasing, from a third-party vendor rather than building from scratch. Common needs: accounting, human resources, customer relationship management. Many vendors have invested millions in robust, feature-rich applications. By buying, you leverage that investment and acquire a powerful system quickly at a lower initial cost than a custom build. Biggest benefits: speed, reduced upfront cost. A product can be implemented in weeks or months compared to years to build from the ground up. Costs are more predictable. License fees, implementation service charges. The vendor handles ongoing maintenance, bug fixes, future upgrades. That frees your team from support burdens, letting IT focus on strategic initiatives. The solution is tested by many customers, leading to higher reliability and greater stability. But the buy strategy has risks. The product may not perfectly fit your specific needs. You may have to make compromises, change business processes to match the software, face user resistance, and suffer decreased efficiency if processes become more cumbersome. Customization may be limited or expensive. Major risk: vendor dependency, vendor lock-in. You rely on the vendor for support, updates, and the future direction of the product. If the vendor goes out of business, gets acquired, or discontinues the product, you could be left in a very difficult position. The vendor might raise fees, leaving you with little negotiating power. Integrating purchased software with existing in-house systems can be complex and costly and is often underestimated. When you decide to buy a commercial solution, the design process shifts from creating technical blueprints to managing a structured procurement process. The first step is to conduct thorough research to identify potential options and establish clear technical criteria, which involves reading industry publications, consulting with information services like Gartner or Forrester, searching online for candidate products. You must define your core requirements, what the system absolutely must do, and create a checklist. This research phase results in a long list of potential vendors and products that appear to meet your basic needs. With your requirements defined, the next task is to prepare a formal document to solicit proposals from vendors. This is typically a request for proposal or a request for quotation. An RFQ is used when you know exactly which product you want and are simply seeking price quotes. An RFP is used when you want vendors to propose a solution that meets your stated requirements. A well-constructed RFP includes an introduction to your company, functional requirements, technical requirements, vendor financial stability, vendor support services, and instructions on proposal formatting and submission. Once you send the RFP to a shortlist of qualified vendors, you will begin receiving their proposals. The next critical task is to validate the claims made in these proposals. Never take a vendor's marketing materials at face value. You must schedule and attend product demonstrations, asking the vendor to show you how the software handles your specific use cases. It is also essential to ask for references and contact current users who are already using the product. Speaking with real users provides unbiased insight into the product's strengths and weaknesses, the quality of the vendor's support, and the reality of the implementation process. After validating the vendors, you must systematically evaluate and rank the proposals to make a final decision. A scoring system is an effective tool for this. Assign points to criteria like functional fit, technical architecture, cost, and vendor viability. Consider hard dollar costs, purchase price, license fees. Consider soft dollar costs, internal staff time for training, integration work, future maintenance. After scoring all proposals, rank the vendors and select the one offering the best overall value. The final steps are to award the contract to the winning vendor and professionally debrief the losing vendors with constructive feedback. The decision between building a custom system and buying a commercial one is one of the most fundamental strategic choices in systems design. Each path has a distinct profile of trade-offs. The right choice depends entirely on the project's context and the organization's long-term goals. The build strategy offers the ultimate reward, a perfectly tailored solution that can be a powerful competitive differentiator. You get complete control over features, the user experience, the technology stack. But the risks of building are substantial: complexity, unpredictability, budget overruns, schedule delays, risk of technical failure or poor management, and long-term maintenance, support, upgrades. The buy strategy offers speed and cost predictability. You can implement a proven, feature-rich solution quickly and often cheaper upfront. The vendor handles development, testing, ongoing maintenance, letting your organization focus on its core business. For standard functions, buying often minimizes risk and accelerates value. The main risk of buying: lack of perfect fit and vendor dependence. The software may meet only 80% of your requirements, forcing awkward workarounds or process changes. You're also locked into the vendor's ecosystem and vulnerable to price increases or product discontinuation. Integration can be complex and expensive. In the end, systems design is the disciplined process of turning an abstract idea into a concrete and achievable plan. It serves as the essential link connecting the business problem defined during analysis with the technical solution built in development. Build a custom application. Buy a commercial package. Following a structured design process is not optional. It is the key to managing complexity, mitigating risk, and delivering a system that works. Structured design. Agile prototyping. Match the approach to the nature of your project, your team's skills, and your organization's tolerance for change. Assess trade-offs clearly when choosing to build or buy. If the system supports a unique process that gives a competitive advantage, control and perfect fit from a custom build can justify higher cost and risk. If the system is for a standard business function where speed and cost-effectiveness matter, buying is usually the wiser path. Consider a hybrid approach. Buy a core commercial package. Extend with small, custom-built modules to handle unique requirements. Remain focused and pragmatic. Start with clear, well-defined business goals. Involve your users at every step. Their feedback is the most valuable resource, preventing mistakes and ensuring the final product is usable. Use models, diagrams, prototypes as communication tools. Write clear, detailed specifications. Design should be technically sound, practical, and resilient. Aim for a system that can be built on time, within budget, and adapt to the inevitable changes the future will bring. Consider strategy carefully. Execute tasks diligently. Stay mindful of risks and rewards, and you can navigate systems' design complexity. Careful planning leads to successful development, deployment, and lasting organizational value.